this lesson, we will be learning how to solve problems using the basic ideal gas law equation. Now, if you haven't already learned how to solve problems using Charles' law and Boyle's law and the combined gas law, you probably should go back and look at other videos to do that first. If you want to, you can use my video called Gas Law Introduction to learn to solve problems with those other equations before tackling the ideal gas law. One of the things we talked about very early on was that with gases we're dealing with volume and moles and temperature and pressure, and so far we've dealt with gas laws that deal with volume and temperature and pressure. We haven't dealt with moles. And the very first thing I brought to your attention when we started this unit was about Avogadro, and Avogadro's hypothesis, or Avogadro's law, deals with moles. Okay, and that part of the gas behavior hasn't been dealt with yet. So what we're going to be doing now is introducing you to the ideal gas law, which includes moles in our equation. So far we've done Charles' law, which is volume and temperature relationships. We've done Boyle's law, which is volume and pressure relationships. And we've combined those two, along with Gay-Lussac's law, to deal with volume, temperature, and pressure relationships. And now we're going to deal with all four of these: volume, moles, temperature, and pressure. And this is the part, this is called the ideal gas law. This is the law that's going to be involved here. Okay? So, we're going to be dealing with volume, pressure, number of moles, and temperature. Okay? Ideal gas law. So let's remember what we said about the combination of gas laws up to now. We said that we had, and this is where I'm going to include Avogadro's law. So we looked at equations and solving problems with Charles' law. And that was volume 1 over temperature 1. Actually, let's do it this way. Volume 1 and temperature 1 equals K. Or volume over temperature equals K. Go back to the original form of that before we started actually solving problems with it. Volume and temperature equals K. All right? And then Boyle's law, the original version. We had pressure times volume equals some K. And we said that Gay-Lussac's law was pressure over temperature equals K. And then Avogadro's law I mentioned, but we haven't put it together like this before, was that, so how do I want to do this? I said moles over volume equals K, but it's also true that volume over moles equals K. Okay? So both that and the original version I showed you on that slide are true. Now, so we can combine all of these together. All right? If we combine all of these together, we're going to get pressure and volume on the top, and we're going to get moles and temperature on the bottom, and that's going to equal some kind of constant, but it's a combination of all these constants. Okay? So there's a special name for the constant that comes from all of these constants together, a special symbol for it as well. And we use the large or capital letter R, and that is the ideal gas or perfect gas constant. All right, so R is the ideal gas or perfect gas constant. And this is one way to think about the ideal gas law. But I can rearrange this a little bit. If I take both sides of this equation and multiply both sides of this equation by moles and temperature, that would cancel out moles and temperature on the left side and include it on the right side. And that will give us then the standard version, the most often seen version of the ideal gas law. And that is PV equals nRT. That's the way you most often see it. Okay? So it's the ideal gas law, and sometimes it's called the perfect gas law. Okay? So it's a combination of everything, another step, even beyond the combined gas law. So let's write down this ideal gas law problem, and I will show you how to go about solving it. We're going to use exactly the same steps we've used with solving all the other gas law problems. And as I said earlier, the only difference here is we won't have a P1 and P2, or a T1 and T2. We're just going to have one P and one T and so forth, okay? So take a moment, write it down, and then we'll start solving the problem. All right, so looking at the problem then, let's write out a list of knowns and unknowns, okay? We've got a sample of argon gas at STP. And what does STP stand for? Standard temperature and pressure. So we know a temperature, don't we? All right, so what is standard temperature? 0.00 degrees C, but we can't solve gas law problems in degrees C. We have to, yeah, so we need the Kelvin version of that, which is 273.15 K. All right, good. And then we have standard pressure. So what's the pressure here? What's standard pressure? 1.00 atmospheres. And we could use 760 millimeters of mercury, or 760.0 torr, or 101.325 kPa. We could use all those. All those are the same value of pressure as this is. And we have a volume here of 56.2 liters. And the first thing it's asking for is moles. So let's just attack moles first, okay? Well, the symbol we have for moles, as I told you before, is N, and we don't know that, okay? Well, if I've got T and P and V and N, I always have R. R is always known, okay? That's the ideal gas constant. It's a constant, so it's known, all right? And I'll show you that in a second, all right? So what I'm going to do is I'm going to write down the ideal gas law here that I'm going to plug everything into. Actually, what I need to do probably is turn this thing sideways because it's going to take that much space, okay? Because we're going to have a lot of stuff kind of spread out. Very often you do with ideal gas laws. So I'm just going to turn my page sideways to do this problem. PV equals nRT, okay? I'm going to make this full screen here.
You said R is what again?
The ideal gas constant. And that's on your test references, okay? So if you'll get out your test references, and you should have that out every day anyway, but it's on the front page of your test references. Okay, you see it? All right. Well, there are actually 6 different versions of it, right? All right, so what we want to do with the ideal gas constant is choose the one that fits the variables or the units of measurement we already have. So let's see. We've got Kelvin and atmospheres and liters, and this one right here fits Kelvin and atmospheres and liters, doesn't it? And we're looking for moles, so there's moles. So that's the one we want to use right there. Do you see that? Now, if you don't have out your test references, and if you aren't looking at it yourself and referring to it yourself, you're not really planning for success here. Let's have those out and do this work yourself. The more you actually put your hands on it and visually refer to your own, the more likely you are to be able to find the right one when you need it on the test. And so now now that I know that's the one I want to use, I'm going to plug that in down here in my list of knowns and unknowns and say that R is going to be 0.08206 liters times atmospheres over Kelvin times moles. Okay? That's the version I want to use. Now, let's go over here and start plugging things in. I've got a pressure of 1 atmosphere. I've got a volume of 56.2 liters. Moles we don't know. That's the one we're trying to find. I have an R value of 0.08206 liters times atmospheres over Kelvin times moles. And then I've got a value for temperature of 273.15 K. All right? And even though I put it up here like this, I really don't even have room. I need more room on my paper. But I'll show you. Well, maybe I should transfer it to another sheet of paper so you can kind of see what's going on here. So we can fit it all on one sheet. Okay, I'm gonna move this work to kind of in the middle of this sheet here. Okay, so I'm gonna leave myself a little bit more room. Write a little bit smaller. 1.00 atmospheres times 56.2 liters times moles times 0.08206 liters times atmospheres over Kelvin times moles, and then times 273.15 K over, well, I will put over one layer. So let me show you how this is going to work then. Let's, what I need to do is to get n by itself. Okay? So I need to be able to multiply this side of the equation by something that will get rid of this and this. That makes sense? Now, that's the same process we use with all those other gas laws, isn't it? We're going to do something to this side of the equation that's going to get rid of everything on this side except the unknown. You with me? So the way that I like to show you doing that is to multiply these things by their inverse, which is what we started doing with the combined gas law, where we had things on the top and bottom. We had to multiply by something and divide by something. So I'm going to take this number and just flip the whole thing over. Okay, so I'm going to have Kelvin times moles on the top. I'm going to have, I'm going to have 0.08206 liters times atmospheres on the bottom. Okay. All right. So this one right here. This term here is the inverse of that. It's just flipped over, and then I'm going to take this and flip it over. 1 over 273.15 K. Now, what that's allowing me to do then is to cancel all this out here. These things are canceled by this, and this is canceled by that. See what I did? Just don't forget that when you do it to this side, you also have to do it over here. So I need to put both these terms on the left side as well. So let's see, I'm going to have Kelvin times moles over 0. Can we see that? Let me get over on the screen so you see it. 0.08206 liters times atmospheres. Okay, that's that term I've put on the left side. I'm sorry. This term right here I've also put on this side. Yeah, it is small. But I'm trying to get you to kind of see the whole thing as well. I don't want to leave you, without the big picture as well. Okay? And then we're going to take and also put this term over here. Huh? The last one over here? This term is just the inverse of that term. Okay? So then I'm going to put 1 over 273.15 K. So I've done the same thing to both sides. These two terms right here, I added to it in order to cancel out this term and leave n by itself. And what I did to this side, I also did this side over here. Okay. Now, let's make these two terms look kind of like these two terms, and then I want to put them over 1. Okay? Kind of makes the cancellation make more sense that way. All right? Well, you should be able to look at that now and see what you can cancel. There's a bunch of stuff you can cancel, isn't there? ATMs can be canceled. What else? Liters can cancel. Kelvin can cancel. Okay, we've canceled all the units we can, and we're left with just the units of moles. Well, guess what N symbolizes? Moles. So we've set it up using dimensional analysis so that we know if we do the math in the calculator right, we should have the right answer. Okay, so our answer is going to be in moles. All right, and we just do the math. Now that means this number is multiplied by that number. You're going to hit enter, You're going to divide by that number, hit enter again, then divide by that number, hit enter to get a final answer. We don't have to worry about the ones because multiplication and division by ones just gives us the same answer we started with. Okay? Now if I use the computer version of the calculator, we're going to get way too many digits here, but I want to use it anyway just for you to see what I'm doing. Alright? We're going to take one, so you can see a simple calculator. 1.00 times 56.2, enter, then divide by 0.08206, so divide by 0.08206, enter, then divide by 273.15, so divide by 273.15. Now I doubt your calculator is going to give you that many digits, okay? So let's just do maybe 5 digits past the decimal on this one, okay? Just to write that much down. So you should have, you'll probably on your calculator 2.507284 at least. Okay? And then that would be, we have units of moles left. Okay, so that's your unrounded answer. Okay? How many significant digits do we want? 3. 1, 2, 3. Underline. Draw an arrow to show that we're rounding off, and arrows are the only operator that's allowed as an operator to show rounding off. So that's 2.5. This 7 makes the 0 round up to a 1 moles. Okay? And there's our answer. Well, whether you want to or not. That was sad. Oh, we didn't finish this problem. That's right, we can't finish yet. Let's go back and look at what the original problem said, because the original problem said we also need to find the mass. Okay? Now that's not so hard. If we know moles, how do we find the mass? Oh, come on, that was the whole last unit. Converting between moles and mass?
Oh, yeah.
Really?
It go from 2.51 moles over.
Well, that would be true if you were dealing with volume, but we're in moles and we want to go to mass. We need a molar mass.
Yeah.
Okay? What of argon, right. Of argon. So argon is Ar. Okay? Argon is a noble gas. So it's not one of the diatomic gases. It's just argon. One atom of argon makes a molecule of argon gas. Okay? Because it doesn't combine with other things. Okay? It's pretty much inert, we call it. And so all we got to do is have the atomic mass of argon, 39.948. No. The diatomic gases are hydrogen, nitrogen, oxygen, fluorine, and chlorine. Bromine is a diatomic liquid. Iodine can be a diatomic gas or a solid, but we usually treat it like a gas just because it makes the math for us easier. Excuse me. All right. So this is the atomic mass of argon. Guys, remember the definition of molar mass. It's the sum of all the atomic masses of all the atoms in the formula in units of grams. Well, that's the sum because there's only one. Okay? And so we have to write it in units of grams. And for us, in this class, you must also include that it is the element argon, or whatever the compound happens to be, and you have to say that it's equal to 1 mole of argon. So we take the moles here, and we put that over 1. So 2.51 moles of argon, and we use this equality statement to convert to grams. What goes on the bottom? What goes on the bottom, I asked, that would be the 1 mole. But you said moles over mass, but it's mass over moles here. Okay? And the mass goes on the top. And the reason we put moles on the bottom here, this side of the equality statement, because we want to be able to cancel moles from this part of the calculation we're doing. All right, so we want to put 39.948 grams of argon on the top. Want to cancel out moles and argon just like we cancel x's and y's in algebra. And we do that math. Okay, so let's see. Where's my little computer calculator here? All right, so we got 2.51. And we're multiplying by 39.948. And that the only units we have left are grams. The species we have left is argon. And how many significant digits do we want? Underline everything else after that, those 3 significant digits, 1, 2, 3. And we write our answer of 100 grams of argon. Now, does anybody besides me see a problem with that number? Well, how many significant digits are indicated by that number? Now, the way I've written it there, there's one significant digit. Okay? How would I show that has 3 significant digits? Huh?
0.00.
If you put 0.00, that's 5 significant digits. All right, good. The easy way, now this is what Carolyn was saying, put a decimal place right there. Now I'm showing all 3 digits being significant. The alternate way to do that, and it's perfectly okay to do it either way, is to say 1.00 times 10 to the second power grams of argon. Okay, either one of those 2 answers would be reasonable. Okay, so we had 2 answers to this problem. One of those answers was 2.50 moles. That was the first one. And here is the second answer here. Either one of those 2 is reasonable. What now? Yeah, these 2 zeros are behind a decimal place and a non-zero digit, so those 2 zeros are significant. However, whenever you have a 0 in the ones place that you want to show as significant, this is kind of a shorthand way of doing it. It's the only case where it works and doesn't come up very often. Okay? But Keller remembered it, and that is this. It sort of simplifies things a little bit. Okay? All right. So here is a problem for you guys to solve. Please solve this problem. Guys, I hate to do this, but we kind of need to move on here, okay? Well, I've asked several times if everybody's done it, and people keep saying they're not. So here's the problem that we were asking you to do. At what temperature will 0.654 moles of neon gas occupy 12.30 liters at 1.95 atmospheres? So the first thing you need to do is to make a list of unknowns and unknowns. Now, what we don't know is the temperature. We do know R, we just got to figure out which one it is. Okay? So you look at your test references and figure out from there which one of these versions of R we're going to need. Alright, so we look at these versions of the gas law, the ideal gas law constant, or the gas constant, universal gas constant, and we want to find the one that matches the units of measurement we have in the problem. Well, we have moles and liters and atmospheres up here, so it looks like this is the one we're going to need right here. Okay? And so I'm going to put R then into my list as 0.08206 liters times atmospheres over Kelvin times moles. All right, now I should be able to at this point clearly see I'm going to be using the ideal gas law. In fact, I should have been able to see that when we started right here. On the list of knowns and unknowns, if I've got temperature, moles, volume, and pressure, then that's going to be an ideal gas law problem. All right, so then we're going to plug in the actual equation here. Here's the equation we're plugging in, and then we're going to plug in the values that we have. So we've got 1.95 atmospheres for pressure here. We've got 12.30 liters for volume here. For N, which is moles, we've got 0.654 moles. For R, we're using the version that's 0.08206 liters times atmosphere over Kelvin moles. And then the temperature is the thing we're trying to find. I got temperature up here in my list as a question mark, so I'm going to leave T in the filled-in equation there. Now I have to solve for T. excuse me, the way to solve for T is to multiply this right-hand side of the equation by something that's going to get T all by itself, which means I need to multiply by the inverse of this. The inverse means 1 over 0.654 moles. I'll put that over here. I need to multiply by the inverse of this. The inverse means we have a fraction that's flipped here. So I'll have Kelvin moles on top of 0.08206 liters times atmosphere. Okay, and what I do to this side of the equation, I also have to do to the other. So when I put both those two new fractions over here and multiply, I've got to multiply the same thing on the other side. Now that gets into be kind of a long problem here. All right, but that's what I've done here. Here's the flipped version or inverse of 0.654 moles. Here's the flipped or inverse version of the gas constant value. And I put both those flipped versions over here on this side as well. Okay? And now we're ready to simplify. Well, by putting these two things over here on the far right-hand side, I can get rid of this term and this term. Okay? So they're all canceling out. I've been able to cancel out everything but T. All right? And on the other side, I've canceled out all of the units of measurement except Kelvin. And because Kelvin measures temperature, I know I probably said that right. Okay? Yes?
Will you be emailing this?
I may be emailing this to you. Okay? Don't ever count on me doing it. All right? Always have your own notes. Because, you know, it might be like I have a meeting or something, or I get sick, or my wife goes to the hospital or something, you know? Oh, there are always shorter ways to do it. Here's the problem. Here's the problem. Shorter ways tend to get students who are just beginning this process lost. Lost gets you the wrong answer. So no, for this class, there really is no shorter way. Okay, for this class, you need to show me all the steps, all the work. Okay? Once you're able to do all the work consistently, then it might make some sense to start looking at shortcuts. But until you can do this and get it right every time, I wouldn't even try to do shortcuts. Yep.
Is your final exam?
Now let's move on here. So if we go then and plug everything in the way you're supposed to, we're multiplying this number 1.95 times 12.30 and hitting enter on the calculator, then dividing by this number here, 0.654, then hit enter again and divide by 0.08206 and hit enter again. We're going to get this number I have down here on the calculator, okay? So I put that on the sheet here, 446.9206913 Kelvin, which we need to round off to 3 significant digits because I have 3 significant digits here, and well, I think, yeah, this one also is 3 significant digits. So those two numbers of the measured and calculated numbers in the problem, those two have the least digits. We want our final answer to have the same number of digits. Okay? All right. We don't have a lot of time, but at least see if you can set up this problem. Okay? Just at least see if you can get to figuring out which equation to use. All right? Before I give you the homework problem. What I want you to do here is to read the problem, determine what your list of knowns and unknowns are, and choose the right equation. You've got 4 equations to choose from. Charles, Boyle's, combined, and ideal.
But does the K matter when you're solving it?
When you're solving it, your temperature has to be in K. Yes.
That's what I'm saying. I'm talking about, okay, you know how you wrote down Charles' law earlier? You put V over 2 equals K. Constant. Constant matters when you're trying to figure it out?
Well, that V over T equals K is the original basic version of Charles' law, but it's not the practical version. The practical version that we use to solve problems is V1 over T1 equals V2 over T2. So in terms of solving problems like this, no. V over T equals K doesn't really matter.
Wait, how do we make it to K?
All right. So if we're looking at this problem, we're seeing that we have the first temperature, 225.0 degrees C, and we have a first volume, 400.0 milliliters, and it's asking for another volume at a different temperature. Well, that would be volume 1 and volume 2. Volume 1 and temperature 1 and temperature 2, and that would tell us that we're using Charles' law. Okay, so here's Charles' law. All right, I made the list of knowns and unknowns. I've already started out with the conversion to Kelvin because you can't use temperatures in degrees C to solve gas law problems. I haven't plugged anything in to solve these problems yet. Okay, but what we want to do then is to take this number for this temperature. So what we want to actually use is 498.2 here, and here we want to use 400.2 up here. So when we plug everything in, volume 1 is going to be 400.0 milliliters, and temperature is going to be 498.2 because you have to have Kelvin temperatures when solving gas law problems. On this side over here, we don't know V2, so we're going to leave it alone. And we're going to put 400.2 over here. Okay? Okay. Let me set it up, and then you can tell me the answer if you don't mind. How about that? So 400.2 in order to cancel out 400.2 on this side. Okay? And if you do it to this side, hello? Yeah, this is you. Yeah. This is the part you were confused about already, and you're not paying attention again. So pay attention. Come on. All right. If I do it to this side of the equation, I got to do it to this side of the equation. This is exactly what you were asking about. All right. So Deja, what did you get when you multiplied this? I'm sorry. Did I do that right? No, I didn't put. That should be 498. I don't know why I put this over here. 498.2. No. That's right. I'm sorry. That part's right. This is right. Okay. 400.0 milliliters. Okay, I was right to start with. All right. So, what did you get, Deja? Okay. And there was no whole, so it wasn't a larger number.
Oh, yeah, there was.
Oh, but that's the rounded number. Okay. So because of time, that's going to be our final answer. I haven't done the unrounded answer, but listen, you have to show me the unrounded answer. If you don't show it to me, that's a lot of points you're going to lose. Okay? All right. Well, I can and I will try, but I never promise because things do come up. So you need to make sure you have these either written down or a picture or something because you're responsible for it, okay?